impulse, with colossal contentment, I would like to welcome our dignitaries, faculty members, students, and all the guests who have graced us virtually for this hands-on workshop. Your appearance has made the atmosphere more enthusiastic. Today, we will be conducting with more techniques and visualizations which were carried out yesterday on data exploration using Orange by eminent guest speaker Khan Muhammad Saqiful Alam sir. So with his tremendous efforts and interest in data exploration, he has accomplished unbounded knowledge in his field. Yesterday, our speaker embedded in us those data exploration hands on skills and covered topics such as data mining and advanced artificial intelligence, machine learning applications, etc. using this software. In today's session, Sir will upskill us with data prediction and data visualization. Join me in welcoming our competent speaker, Khan Muhammad Saqiful Alam sir. We are once again blessed to have your desiderated presence in our event, sir. We are all excited and eagerly waiting to know more about data exploration. So, without further ado, I would now like to invite Khan Muhammad Saqiful Alam sir to continue ahead. Sir, handing it over to you.
Thank you so much, Nidhi, and thank you for the introduction. So just to recap on what we have looked so far, we looked at how like softwares like Orange can help us run Python codes without even writing a single line of code. Because like, I'd like to refresh that Orange is a graphical user interface on top of Python, and we looked into how to load the data, how to like query the data, group the data, transform the data, pre-process the data, as well as how to impute blank or null values. Now, when you do the preparations of the data, the next step, the obvious next step, is actually working with finding out insights from the data. Now, we will be sticking to the previous data set we shared because, we have been working on that to start with. So I'll just start sharing my screen now. Here. So I'll just repeat one of the steps that we did in the last session, which is loading the file, the CSV import. So if we start by loading the file, double click here and choose the file we have loaded. Now, the beauty of Orange IDE is that the stuff that we did last time in terms of loading the file, that is, declaring each of the columns and what these columns mean, which are numeric column, which are non-numeric column, which are date time column, all these are already stored in Orange. So when I press this import options, you will see that this is exactly how we set our file. The columns which are non-numeric, the columns which are numeric, and the columns which we skipped. So we don't need to redo our work here anymore. Now, after loading, let's go towards visualizations. Now, visualizations, before we jump onto visualizations, I will give you some simple insights into how to go forward visualizing a data set when you start with it. Now, we live in a time where you might have seen many complex and very beautiful visualizations. So this will come as a surprise, as an advice, if I tell you that most of the schools of good visualization actually prefer simple visualizations over complex ones. So, for example, I am actually one of the board committee members of this association called Data Visualization Society, DVS, and right after your session today, we're having our monthly board meetings. So one of the things that we work with is actually setting up a standard for visualizations across the globe, across the globe. And what we have seen again and again and again is that a simple visualization sometimes can do 90% of the job. We don't need to go for very complex ones. In fact, we do discourage complex visualizations, not the ones that are really beautiful, but like we have seen a lot of like a visualization that can be eye-catching to look at, but then the moment we try to get an insight out of it, it sort of gets lost. So that's where I think the suggestion is to go for as simple as possible to start with when exploring, but also to be as extensive as possible. By extensive, I mean when you're exploring a data set, when you don't have an exact expectations from the data set, you're just starting with an exploratory analysis. The key to a good exploratory analysis is the detail. So what do we mean by detail? By detail, we mean looking at each and every single variable at a time, and then checking the each and every variable's relationship with each other. So before even working on the visualizations, let me actually show you in Excel. So it's actually one thing I was like I had an intern who I was teaching how to do a thorough visualization, like exploratory analysis, and I was teaching her this technique. So suppose you have a data set which has say 4 variables, say column A, B, C, and D. So with say 4 columns, and regardless of how many rows you have, then how many visualizations or how many explorations should you do with your data? The answer is very simple. You start with single variable exploration, looking at single vars, single variables. So by that, you can look at, first of all, you can just explore A as a variable, B as a variable, C as a variable, and D as a variable. These 4 charts. So this is 4 here. Okay. But then do a bivariate relationship. So check with AB, then with AC. BA is covered, so BC, and then BD. Is CD. So you have how many combinations? 1, 2, 3, 4, 5, 6 combinations here. You'll know this through permutation calculations, but just going through on hand showing you. So that basically means that when you're done exploring each of these individual variables, explore how each of these variables interact with someone else. Then you can go for more complex, looking at A, B, and C relationship. So there are combinations of 3, but by the time you've individually looked into each variable and gone through pairwise relationship of each of the variables, you will most definitely identify which variables have some information in them, which variables are important for your analysis, which variables you can stop, might not work with because that's not very useful. This is what we say the approach towards exploratory analysis, that exploring one variable at a time. Very useful, very important. Now let's move to orange. Now, how do you just explore variables? What are the tools you have for exploring variables? In my opinion, the 2 most simplest tools to explore a variable. So in terms of variables, you can have a numeric variable and a non-numeric variable, a categorical variable. Text, you can visualize, but text is not that, cannot be summarized, so you can skip that for now. So if you're doing a exploration of numeric and non-numeric variables, for individual numeric variables, it's very important to do simple distributions, histograms. One of the most useful tools in your data arsenal, in your exploration arsenal. For non-numeric variables, for categorical variables, a very useful tool is the bar plot or the bar chart, or you can also call it column charts. So it's another very useful tool. So let's first look at distributions, how to do histograms in orange. So we bring in this and we connect our file with this, and you already have these distributions. Now the beauty of orange is they have already guessed whether it's a numeric variable or a non-numeric variable. If it's a non-numeric variable, it's just giving you a frequency distribution. So for example, we can see that, okay, among the age group, the dominant age group is middle, followed by young and old. Gender-wise, it's equally distributed. Own home-wise, it's almost equally distributed, though a little dominated by people who own home. Marital status-wise, it's equally distributed. Most of the people coming to this shop are from nearby regions. Children distribution, interestingly, like something we would expect equally, that, you know, most of them don't have children, some with 1, 2, and 3. History distribution is also a little dominated by high, then low and medium, though if you remember that there were missing values in history. Now, what about the numeric distributions? So for the numeric distributions, you can look at salary. So salary has a very skewed distribution, and a very, the type of distribution we call them is like, you know, one end fixed distribution. Why? Because no one can have a negative salary here, right? So the lowest you can have is 0. So it's a limited width distribution. The maximum is unlimited. People can have really, really, really high salaries. In fact, from here, you can actually pick this person out and see who this is. So the way to do so is, say, besides this distribution, you can again create a data table and say, open the data table here, open the distribution here. So have both of them into screens. So this is in one screen. It's here. Now, the moment, and this is where it's very interactively useful in Orange. Here, this tells me that these are the people, like this is the person who had a salary of greater than 16,500. So this is like, you know, oh, this person is old, male, who owned his own home, is married, lives close by, has a very high salary, no children, a high history of coming to the shop, few catalogs, and spent quite a lot, 1,512. Now suppose I want to see those who has, like, you know, those people who have earned more than 1,000 and more. So I can just drag from, say, 1 million, and here you just drag this. Let's drag again here, and then check out selecting this. Let's double click the data table. So these are the selected people. So here there are 98 people who are above a salary range of 1 million a year, and this is 100,000 a year. Yeah, and these are their full data. So not only can you visualize data here, you can also select and look at the subsets of data here as well. Now, the other thing we can do is also try fitting distributions, because sometimes when we look at a numeric variable, it might be useful to see whether the numeric variable follows a specific statistical distribution. Why is that? It's because if we want to build a simulation model of how, say, people with different income spend in my shop, instead of just looking at existing data, suppose I want to run, like, using this data, I want to build a simulation model. And for this simulation model, I can then choose to do a simulation for, say, 1 million people, and then maybe make changes and then see how the shop behaves based on a simulation model. Then we need to fit the numerical variable in distributions. That way simulations work the best. So we can check what sort of distribution. Now, just by experience, I would say this is not a normal distribution, right? Because a normal distribution would be skewed in the middle, small amounts the left and the right. This falls more towards a beta or a gamma distribution or an exponential distribution. So if you try to fit a normal distribution, you get, it's a mean of this and a standard deviation of this. But if we get, like, say, a beta distribution, I think this better fits it. So the beta distribution would fit this data, like, you know, model this data better. If we see how a gamma distribution fits, somewhat similar. Or if you look at an exponential distribution, maybe not, because exponential distributions don't end, and this one does have an endpoint. So I think a beta or a gamma distribution would make it a, like, you know, or even if you look at kernel density, nah, not that a good fit. A beta or a gamma distribution could be a good fit for this data. Now, this is another additional function you have with orange, is that, fitting a distribution, but let's fit with none. Now, we can do the similar ones, say, by catalogs. And in catalog, it's sort of like a uniform distribution, obviously. And spending amount, I think, has more commonalities with normal distribution, though gamma distribution or beta distribution also does a good job. So at least we can fit in a normal distribution almost in the spending amount. And here again, we can also identify those people who are my super spenders. These people. So if I draw a line here, like these groups, above 4,000, let's see who are these super spenders. There we have 13 super spenders in my shop with spending amount which is greater than 4,000. And these are the people. So if you remember, from here, we can create subgroups and then compare subgroups using the Venn diagram, that who fits. So for example, say, okay, let me just give you an example. Say these are my high spenders, right? So let's just keep them selected. Let's just have another distribution function. And from here, let's say I also figure out those people who are earning more than 100,000 a year. And let's get another data table here. This is the second group. So this I can call as my high. And this I can call and then see how many are common between these two groups. So we have an error coming here. And what is that? Some variables have been renamed to avoid duplicates. Okay, sure, fair enough. So actually there is quite someone common, 13 people common among the 13 high spenders and the 98 high earners. So that basically means that almost out of the 13 high spenders, almost 10 of them are coming from people who earn a lot. So already we do have an understanding of the relationship that, more the salary, more the spending, which is proven by the fact that there are 13 high spenders. Out of them, 10 of them are from people who earn more than 100,000 in a year. Now, this is a very simple, exploratory visualization we looked into. These are single variable distribution, but at the same time, we can use distributions to find multiple variable distributions as well. So let's look at age, and let's just remove these as we'll be getting continuous errors. Let's stick with one of these. Now, we can divide age. So we can split age by, say, another categorical variable, say gender. This shows my age distribution divided by gender. This is what we say a stacked column chart. Not stacked. What's it called? Dodged column chart. So dodged because we're keeping two bars separate from each other. And here it shows that, okay, in all the three groups. So in the old and the young group, it was the female customers who dominated, but in the middle group, it was the male customers who dominated in terms of number. Now, what we can do is we can also put that as stack charts like this. So this shows the proportions. We can get an idea of proportions, but this can be a little misleading because, I mean, if you're just looking at proportions, it could be like this red bar is higher or this red bar is larger, but in terms of like overall young populace, maybe the red is not as proportionate to the blue compared to, say, this one, where the red is less proportionate. So if we want to find out that for each of the age groups, what is the gender distribution for each of the age groups? I think another very useful function is show probabilities. Here, what we have is now a fill bar chart or fill column chart. And here, instead of looking at how many in each group, we just get out of 100%, in the middle, what is the percentage of female, what is the percentage of male? In the old group, what is the percentage of male and what is the percentage of female? In the young group, what is the percentage of male and female? But when we look at this graph, we have another issue. That issue is if we were to compare the total numbers, this is not visibly comparable because all the bars of the same height, all the columns are of the same height, which is 100%. So the comparison or comparability across the groups is gone. Just comparing the proportion within the group. If you want to compare across the group, I think the better choice is sticking with a dodged column chart or a dodged bar chart. You can do the same with, say, gender. Say, suppose you have gender and we shouldn't split by gender. In that case, it doesn't make sense. Let's say gender and, like, marital status, just to see what's happening. So for the female gender, single is dominant, whereas for the male gender, married is dominant. If you look at, say, history of how regularly people are coming in, and say we divide history based on age groups, and we see for high history is predominantly dominated by middle-aged group customers. Medium history is also dominated by middle-aged group customers, and it's a low for the low history, it's mostly the young age group customers. If I want to see for each of these groups the proportion of customers, then we can do a stacked and a probability just to see which group dominates in which of the histories. So it's actually medium, which dominates both the medium and high history, whereas it's a young that dominates the low history. If I ask the question that, okay, which group in which of the histories old age people are dominant, it's actually high again, followed by medium, and finally the smallest subgroup of old is in low history. So this is how, besides just looking at a singular distribution, we can look at multiple distributions. Now, we can also look at some bar plots. But before bar plots, actually, before we go to bar plots, I'd like to spend some time on a box plot. Another super useful visualization we have in our arsenal. Now, what a box plot does is, for example, if you're just looking at ages distribution, it just shows how many people are from age group. But let's say we look at, first of all, we just look at, say, the spending amount, or say the salary. So oops, the salary is not here. Oh, here is the salary. So let's look at the spending amount first. Now, what a box plot does is it gives me few information about a singular number. So this is another very useful visualization for numeric variables. So it starts with my range. Like, this is the range of values I have. Then it starts with, say, the middle number here is 12.16.77 is the mean. And this is a standard deviation. This, the yellow number here, is the median. And then we have the 25th percentile, the first quarter, and the 75th percentile. This basically means that the data set we have, 25% of them spends less than or equal to $488 in a month. This number means that of the data set we have, approximately 25% of the people spend 1,689 or more. 962 means that 50% of the people spend less than 962, 50% of the people spend more than 962. Now the solid line here is the local outlier factor. It gives you a plus and a minus values of, like, positive, like the highest and the lowest values statistically possible, or statistically should be like considered a normal value. Anything beyond that are outliers, which gives you an idea that, okay, this variable, the spending amount, has some really high ranging outliers, whereas it doesn't have too many low ranging outliers. And the high ranging outliers are values beyond 2,200-ish. So now, not only box plots give me a good idea of, say, a single numeric variable, but if I divide the box plot into multiple categories, we can do that as well. So let's say we divide this box plot of spending amount across age groups. Now I get a very interesting insight. So who spends the highest in my shop statistically? It's actually the middle and the old group. Because look at their box plots. They're very similar to each other, and both of them are very different from the young group. In fact, if you look at it, they've already calculated a between group ANOVA analysis of variance, and the p-value is almost zero. That basically means that the null hypothesis of ANOVA here is that there is no difference of spending among the three age groups. And the alternate hypothesis here is that one of the age group is different from, at least one of the age group is different from the others in terms of spending. And the probability of null, like not being true, is almost 0.00, which means we go to the alternate hypothesis, which means that you can confidently and statistically say that at least one of the groups, and here we can see from this diagram that it is the whole young group whose spending amount is actually significantly different from the old and the middle group. We can actually explore amount spent like that across other categories. Like, is there a difference between gender in spending? Yes, the students see the p-value is zero again, which means the probability of null taking place is very low, which means that it will be the alternate hypothesis. Here again, the null hypothesis would be like there is no statistically significant difference between the spending of the male and the female customers. And we can see that the male customers do spend a little bit more compared to the female customers. What about own home? The people who own home significantly spend more. What about married? People who are married significantly spend more. What about location? Again, there is a difference. And interestingly, it's the people who are coming far away who spend more in the shop compared to the ones who are close by. Which sort of explains, because I mean, you're going to a grocery shop or a supermarket. If you live close to the market, you'll visit more often, right? And spend small amounts each time. Whereas this one is the fact that people coming from far away do end up spending considerable amount of money. Now, what about children? So interestingly, having more children does have an impact on spending, which is interesting given the fact that having more children has lower impact on spending. So the more the children, the less of the spending, which kind of makes sense because I mean, the more children you have to be a little picky about what you want to spend on because you want to minimize your overall costs. What about history? So people with missing history, let's skip that. Let's look at just low, medium, and high history. Obviously, I think it's very obvious that people with high history do spend more compared to people with low or medium history of travel, like coming to the shop. So we can do these individual comparisons, like for each of the numeric variables. We can do the same thing for salary to see, like, is there a relationship between salary and the number of times people come? And yes, high history people do, like, have more money compared to low history. What about if we say salary and children? Well, there is no relationship technically. What about, say, salary and gender in the data set we have? There is a relationship that male average salary is higher than the female average salary. Interestingly, this is like, US data, and still there is a level of discrepancy here. What about the age group? People with the middle age group are the higher earners and the young age group lower earners, which kind of is expected. So this is how we can individually check each and every numeric variable and how their relationship is with the categorical variables. Now, let's look at another visualization which is handy, is the bar plot. Now, bar plot is mostly for, say, we can group these salaries, say, or the spending amount by, say, age, and say color it by, say, age as well. So this shows, like, individuals. So they are not doing a summation anymore. This is like, each single bar for each, like, for each data point. So here the bar plots are actually per data point visualizations. So we're looking at, like, like all the middle age people spendings, all the old age people spendings, and all the young age people spending. How is this helpful? It actually helps me figure out that, okay, this person, although he's a young group, is quite a heavy spender. In fact, what we can do is, like, just identify this person. Let's say we draw a data table here and say open the data table and have the bar chart open as well. Now let's look at this heavy spender in the young group. This person is a female young person with 68,000 salary. So that's quite a good salary, I would say. Um, High history, has received a lot of money, like a lot of catalogs, and yeah, spends pretty high in my shop. So this is like the bar plot is a good one to quickly look into, say, individual data points and those that stand out. For example, I think my high spender is this person. Let's select this person. He's my high spender, and we can see him here, the old female who has spent a lot in my shop. Now, besides bar plot, we can also have a few other plots, which is like the sieve diagram and the mosaic plot. So let's look one at a time. Let's look at the sieve diagram first. What does it do for me? So the sieve diagram allows me to compare two categorical variables. So suppose in one case we have the age and in one case we have the gender. So what we get in gender and age, here we see that there are 302 people in the male gender, then and in the middle age group. Then we have 76 people in this group, which is like our age is equal to old and gender is equal to male. So this is showing a chi-square distribution as well. So this chi-square distribution talks about equal distribution or non-equal distribution. So the null hypothesis tells me that the age and gender are equally distributed. That basically means that there is no dominant gender in either of the age groups. That is, age is not dependent on gender, or the gender is not dependent on which age group it is coming from. So the null hypothesis would be like there will be equal distribution. So which means like, for each of these groups, so male, there would be 33% old, 33% middle, 33% young, female also 33% middle, old and young, so equal distribution. But in reality, it's not the case. So we can see that in age, in the middle age, so the male is this person, this much, whereas the female is 206. Then again, the old age, male is 76, female is 129. So not by the size of this, but by like this is showing the distribution. This shows the chi-square value. So this is good at comparing each of the like two categorical, like comparing two categories. So for example, if you look at gender and say by let's say history, this is what we get. So here again, the chi-square is like null is almost 0, which means that the groups are like the history is actually dependent on which age, like which gender you're coming from. So here we get like, we can score like distribution, like chi-square distribution. So for example, amount spent in history is having the highest chi-square value, followed by amount spent on salary. Then so what this tells me is this like high chi-square values mean that the dependency among the two variables are high, which basically means that for amount spent really depends on how many times people are coming to my shop. Amount spent also depends a lot on salary. History depends a lot on salary. Age is also connected to salary. Marital status is also connected to salary. Age is also connected to amount spent, and amount spent is also connected to married. So this kind of gives you all the combinations. So for example, these are not connected at all. Like say we say that, okay, gender and location, not connected at all. The gender is not dependent or connected to location whatsoever. So it doesn't mean that means that, location doesn't play in determining which gender my customer is, or vice versa. Location and married. Location doesn't play a role in saying that which customer should be married or not, and vice versa. In these cases, the chi-square is very low, and the probability of null becoming like not null holding is very high, 82.6%. So this a score combination is a very easy way to figure out like it's very useful in exploring, because it gives me an idea that which of the variables, like like pairwise relationships are important, which are the pairwise relationships that are not that important. So if you remember the Excel file where we say that for 4 we have like 6 combinations, so you can do a quick hand calculation to find out like how many pairwise comparisons we can do in like with 10 variables, and out of the pairwise comparisons we can see that approximately 30 of them are relationships that matter. Beyond 30, you see that the p-values are increasing and the chi-values are reducing, which means that the chance of these two variables being related to each other, the test of independence, is failing here. That these two are not dependent on each other, these two are independent of each other. So this gives you an idea of, like, how many pairwise combinations we can have, pairwise relationships we can have. Now, beyond sieve diagrams, another useful one is mosaic plots. Let's look at that now. For mosaic, it's more like if you're interested in not just one, but say multiple, like not two, but multiple dimensions. So for example, here they're showing an age and a gender distribution. But what if age, gender, and I want to look at also marital status distribution, where these bars are representative of each of the ratios of populations here. For example, these are male married, these are male single, these are female married, and they're from the middle age group. Now that these are from the old age group, and these are from the young age group. And the coloring is done by the number of people in there. Then we have, we can actually bring in another variable, say whether they own home or not. So this visualization can quickly become a little complex, sorry about that, but it gives you an idea of, like, how multiple numeric and non-numeric variables are connected with each other. We can also put in numeric variables here. And then the numeric variables would be like, put in bins or groups. So we can also put in, say, amount spent here. This becomes quickly pretty complex. Now, again, a good idea is you can actually ask Orange to suggest you informative mosaics. So you can decide that, okay, at most you look at 4 relationships which are really insightful. That is, that creates visual differences among them. And then just press start. It's going to run through the whole data set of 4 combinations. You can see that there are many combinations coming up, because you know that if you do comparison of 4 permutation possibilities of, like, 10 variables, you will get a lot of tests. You won't have to worry about it. Orange does its job. So it suggests you that one of the most, like, visually discriminating combination would be amount spent, married, own home and salary, followed by age, married, own home and salary, followed by amount spent, history, own home and salary. And the ones that are least informative are ones like this: children and married, catalogs and date of visit, children and location, where the groups are of similar size. So that's what Orange does for you in terms of mosaic display, very similar to sieve diagrams. Now, we do have one of these, which is like line plots. So if you look at the line plot, it's mostly useful if we look at line plots in terms of, like, like date time data. So say, for example, what it's doing is it's just looking at numeric values here. But let's say if I just have, say, divide them by gender, married. So not much information here, because line plots are better for time series data. So we don't have too much time series data here, and we can work with time series in the time series add-on. That gives me a better idea of, like, line charts. So for now, I'll skip the line plots here. Now, I think the last and one of my most favorite visualization is scatter plots. It allows us to look into relationships between 2 or more variables. Scatter plots, like the key scatter plots, originated by comparing numeric variables, and that's what we're going to start with. Let's say we call X variable as salary and Y variable as spending amount. Now, what we get here is a scatter plot showing that, okay, more the salary, more the spending amount, which means that, there is a positive relationship between spending amount, salary and spending amount. So people with more salary will spend more in my shop. Now, to start off with, one thing you notice is if we work with the opacity here, the opacity is important because it gives you an idea that where more values are condense and where there are less values. So if you look at these places, there are some overlaps. These are singular numbers, and these are the concentrated areas of my data set, which is that most of the people are here, some one or two here, and then there are some around this place. Now, before I add any more dimensions, I would want to show you first a very useful analysis we do when we look at scatter plots. This concept is not a very mathematical concept, rather a conceptual thing. We call it a quadrant analysis. So quadrant analysis means I can design, like I can build 4 quadrants in this scatter plot. So what we can do, the way to design these quadrants, so I don't think I can annotate here in, can I? Let's check. I don't think I can annotate here in Teams, but that's fine. I'll give you a simple idea through here. So one thing we can do is say, let's assume that anything of spending of 4,000 in a month and above is high. So which means I can draw a line here. Then again, we can also assume that anyone who's earning more than say 120,000 a year is high earner. So you can draw a line here as well. So if we draw a line here and if we draw a line here, we will be dividing the scatter plot into 4 quadrants or 4 parts. This would be like, high salary, high spending. This would be high spending, low salary. This would be low sal, low spend. And this would be high sal, low spend. How is it useful? So as a customer, like, if someone's analyzing the data of this company, I would want to figure out people who are high salary, low spend, people who are, I would say, Scrooge McDucks, people who earn a lot, not spending in my shop. Who are they, and what can I do to make them a high spending dot? So these 2 are my points of interest here. So let's select these 2 and let's see who they are. Who are my Scrooge McDucks? Here you go. One male, both of them male, from middle and old group with quite a lot of salary. One of them comes quite regularly to my shop, but still not spending enough. So now that I know this person, I might actually look up that person in the shop's database to find out what is he purchasing and why is he not purchasing enough. What can I do to make this person a high spender? Because he does belong to a group of high salary people, just don't spend much. This also helps me identify my unicorns. So I call them unicorns because these are people not high salary. So these few, they are not high salary as these. They do spend, like, they are heavy hitters. They spend a lot. Specifically, these 3 would be my unicorn. Maybe this 4 or even this person. They're not that high in salary, and yet they do spend a lot. So this 5 of them are my unicorn. Who are they? So the salaries are borderline high. All of them coming from PAR, all of them owning a home, all of them married, and all of them regularly visiting my shop, and their spending is stellar. So this was the real data, and actually we found these unicorns, and there was this. So I'll apologize in advance for a very, like, it can be a little insensitive joke, but still I would tell you like the real story here. So since this was a shop we were talking with, it was a project I was doing for the shop, and this was real data, and we found out that people who are my unicorns were all married. So the manager of the store was like, okay, can we just start a matrimony service in our shop? Because as you can see, the people who get married also spend a lot of money. I was like, very interesting insight, but I think it's the chicken and egg. I feel like it's just because they are married as a couple that they're spending more, not that being married has anything to do with spending. So this is another interesting insight. So this is what we call quadrant analysis, because the other quadrants, like the high salary, high spender, is an expected dot. I'm not surprised. At the same time, the low salary and many of the low spending dots are expected as well. It is these ones, the unique quadrants, like the unicorn quadrant or my Scrooge quadrant, who are more interesting, because the unicorn quadrant is my learning of, so I can pull these people up to find out what are they spending for which they're unicorns. I might track them over months to see, do they stay unicorn? If they do, then maybe they're buying something or they're doing something which is making them spend a lot in my shop. For the Scrooge, I need to figure out who that, like, what's happening with that person, with that group, and why are they consistently being Scrooge? If a Scrooge moves up to a normal person that is like this quadrant here, if this point goes up here, that's fine. I'll just be like, okay, in 1 month he was maybe counting money a little bit or being careful a little bit with his expenses. That's fine. So this is one very interesting way of checking data. I think I would say that when I was going through my undergrads, I never thought that you can build like such simple quadrants and compare data and tell such story with the data, but you can do that. So let's reduce the simple size a little bit, and because I'm going to introduce more dimensions now, scatter plot. Now the next dimension we can do is the color dimension, and let's look at the age group distribution here. So an obvious, fast, quick, simple insight that young people are cluttered in this area of low earning and low spending. My Scrooge is an old person. My unicorn is both old and young. So my high spenders are distributed among old and middle. There is only one young unicorn who's around here, and there are a few Scrooges of young Scrooges here. But mostly the blue and the red is well distributed, whereas the green group is mostly in the left side of it. Now, there is another very useful tool in Orange that kind of helps me identify, like, color-wise, is there any segregation within the data points? And the way to do so is just clicking the color regions. If you would see the color segregation of the gradient, the dominant color gets the background color as well. So the dominant color of green is in the left, most left in the downwards corner group. These people, which means that the low earning and low spending is dominated by the young professionals, whereas the blue and the red did not, like blue dominated the rest of it just because young middle group was the highest in appearance, though there are some small reddish clusters here and there. So this is very useful when we are looking at, like, if there is a dominant cluster available within the color groups. Now we can also do shape. Let's call the shapes in terms of gender, in terms of male and or female. We can do size in terms of, let's say, the number of catalogs they receive. So this is another very interesting insight here, that we could have guessed initially that people are given more catalogs who earn a lot of money. Not really. The shop has given catalogs, high numbers of catalogs, to people who don't earn a lot of money as well. And we could have expected that the more the catalog, more the spending. Again, not really, because there's a lot of low spenders with high number of catalogs. And then there are a lot of high spenders with absolutely no catalogs. But an interesting point would be to see that, giving this Scrooge a few catalogs, would he move up there or not? Now, label we can put in, this might actually become very messy if you put in labels. Actually too many labels, so they're asking like to zoom in to find the labels. I think we can just skip with the labels, or we can actually choose label only selection and subset. So now they'll just show the labels, or now they just show the labels. Now they just going to show the labels. So we can actually choose labels as let's say children as well. And okay, how many children's here? So if you're just looking at, like, how children's might have an impact on spending. So for example, the low spenders, actually quite, like, on average more children. For high spenders, let's say less children. So yeah, having number of children's do impact high, like the difference between high and low level spenders. So this is quite a lot of things we can do with this scatter plot and get quite a lot of insights. So it's actually one of my favorite visualizations out there. Now, another very useful, I would say, exploratory visualization is something called FreeViz. Now, to work with FreeViz, you first need to create some additional information, or give some additional information to Orange. The additional information we need to give Orange is actually this idea of selecting columns. Now, so far, if I give you an idea, we have selected 11 features, and our features look like these. These are the informations that we have given Orange. What we haven't told Orange yet is which variable is my target variable. Who is my variable of interest, and who are we going to use to predict that variable of interest? To do so, I need to declare columns and their roles. What I do is, using the CSV file, I connect it to select columns, and here what we do is we first identify the columns here. Say in this case, my target would be spending amount. I would like to use these variables to make a prediction of how much people are spending. And let's say we're going to ignore the last date of visit, not that useful information to make a prediction, because I mean, people don't spend based on days. People spend based on different qualities. They have different, say, different subgroups they come from, or different characteristics they have. So when I declare this, I'm telling Orange to ignore one variable, use these variables to make a prediction of this variable. The target is spending amount. Now that I've selected the target and everything, we can go towards our freebiz and connect it here. So there is a warning sign that categorical features with more than 2 values are not shown. So it can only handle categorical features with 2 values, which means that age is not shown and history is not shown, but everything else is shown. So what it does is, if I try to predict amount spent, then if I start here, press start, you'll see something very interesting going on. It will take some time, but it's not going to take like it's at 1% and it's going to build it to 100% very soon. It's not going to go like the time it takes from 0 to 1%. That's gonna be disastrous. So it speeds up later. There you go, done. So what is this? Okay, so first of all, look at the colors. The coloring is based on spending amount. Blues are low spending amounts, and the yellows are high spending amount. Now let's increase the opacity a little bit. Yeah, there you go. And reduce the symbol size a little bit to make this readable. What's happening here? So say own home can be 0 or 1, where 0 means whether someone is 0 means the person is so own home can be own or rent. So they do 0, 1 based on alphabets. So if it's own, O, and then rent is R, O comes first. So that means 0 would be own and R would be rent would be 1, which means as the data moves from own 0 to rent 1, overall amount spent moves towards the lower side. So this tells me that spending amount reduces with own home moving from 0 to 1. Or the other way to put it is, as people rent more homes, they spend less. Let's look at married. Married can be married and single. So alphabetically M and then S, which means as people move from married to single, so single people tend to spend less in my shop. Gender, male to female. Now, these directions means that own home and married, if you see that they are in the same direction as that of smaller numbers of amount spent, right? Blue means small numbers, which means that these two variables overall impact smaller spending more. Or the simpler way to put it is that marital status and whether someone owns home or not highly impact amount spent. And in fact, not only they impact amount spent, we can also say that, okay, if you rent a home, you're more likely to spend less, and if you are single, you're more likely to spend less. So they directly impact your spending amount. Gender, in this directional graph, gender is somewhere in the middle. So which basically means that gender has not too much effect because the blues are concentrated here, the yellows and the greens are concentrated here, which means that gender has not too much of an effect. Now, what about the other ones? Salary. Salary has a direct linear effect on the spending amount, because the greens and the yellows are here and salary is increasing here. So the more the salary, 0 to more salary, the more spending. More catalog, more spending. Location, again, it's near and far. So far and near. So far and close. So close is first C and then far is F. So which means C is 0 and F is 1. So more like, the people are far away, the more they spend. So this actually is another very useful way to look at how different variables impact your spending amount, your target variable, how the other features impact your target variable. So it's called FreeViz, quite a useful one. You can also work with, say, RadViz, which is another form of FreeViz, but gives you a similar result. So, but I mean, this is where I would say that, visualization is getting more complex than meaning sense. So I'd leave it here. So these are basic visualizations we can do with Orange. Feel free to explore with more, but I think the ones I have showed are good enough for a good starting point. Now, let's go towards another use of Orange, which is modeling, building models with Orange. So what I'm gonna do is I'm gonna clean these out a little bit. Keep the select columns because when modeling, I need to decide what I'm going to predict and what I'm going to use as variables to make the prediction. So here, this select column tells us that, okay, we're gonna predict amount spent using these features. Now, building on, we now can create different models. But before creating models, what we're going to do is first we can see what sort of models we can fit. So there are many models available. So for example, there is a constant model, which actually gets from the data set the most frequent class. So it's a classification model, which picks up the highest class of the prediction. Then we have naive bayes model, which uses Bayesian statistics to make predictions. We have linear model, we have random forests, we have trees, we have boosted models, we have neural networks, quite a lot of suggestions. Let's start with a very simple one, a linear regression model. Let's say I want to build a linear regression. And in the linear regression, I just decide whether there is a regularization. So regularization means there are a few types of regularization. Ridge regularization, lasso regularization, both of these regularization, and elastic net is a combination of both. So these regularizations, what they do is they simplify the model by penalizing the number of variables in the model. So, instead of say 10 variables to make a prediction, they try to make a prediction out of say 4 variables or 5 variables, and any other variable that do not add too much to the prediction are dropped off. So one good way is carrying out what we say is elastic net regression, which basically ridge and lasso are different ways of penalizing excess variables to make in a regression equation. And elastic net is basically 50% of they do the penalization in a weighted way. They do ridge 50% of the times, they do lasso 50% of the time. So that's how they do regularize. So here, one problem with Orange, or one limitation, is you cannot see the regression output here. Okay. So normally, I think even the educational ones, they don't have, they don't have regression outputs here. So because Orange is not about interpretability or fitting regression, multiple regression models and then explaining regression models. Rather, Orange is about building models. So now that I've fit a regression model, how do I see that this is this model has been useful for me? So what I can do is go to this evaluate tab, and I go to this thing called test and score. So what it does is I connect this, and also from the columns, I connect the data here, and it does a testing. It tests how my data fits, or how my model is able to predict the spending amount. So when I open this, first of all, what we are doing here is something called cross-validation. So what cross-validation does, k-fold cross-validation does, if I show it using Excel here, let's say if I have a full data set, let's say this is my data set, I'll use colors to do it. Say this is my data set. 2, 3. Say this is my full data set. And like what cross-validation does is takes one of these. So it's going to separate this into one group. Let's call it test group. And then it's going to divide the rest of it as train group, training data sets. And then it's going to pick up, like, divide these two into, like, this data set into two parts. It's going to train a model in these parts 1, 2, 3. I'm sorry, 3. So let's say it takes 6 apart, and it takes, let's do. Yeah, so it takes parts 1, 2, 3, 4, and 5. It tries to fit a model here using parts 1, 2, 3, 4, 5, and then checks its accuracy in 6. The next thing, so this is what we say round 1. And in round 2, it does the exact same thing now. But say, let's just format painter and paste the format here. Okay. But now what it does, it takes in 1, 3, 4, 5, and 6. These 5 parts as test training. So it trains the model here and tests it with, say, part 2. Then say in round 3, it's the same thing again. So we just use a format painter here. So it again divides the data set in 6 parts, and now it has divided the data set in 6 parts, but this time, let's say it picks up 1, 2. So from these parts, it fits a model and then tests the model's performance in part 3. So as you can see, we can go like this for 5 rounds. So we have actually 6 rounds. So we have round 4, which is similar. So we just do the format painting. And say the data set goes to 1, 2, 3, 5, and 6, and then fits a model and then tests the model's accuracy in part 4. And then we do round 5 and round 6. And then what we do is using these 6 tests and 6 models fit, it combines these fittings to build a final model and test the score of these models. And what it does, it tests something called the root mean squared error. So the RMSE or the MSE, as well as the R squared. So the root mean squared error is a measure of how much error each model has. So the way root mean squared error is calculated, if I give you a quick overview, is say we have the actual data, model prediction. Say, just for the sake of it, let's say the actual spending of someone was 120 and 150. Model predicted one to be 100 and the other to be, say, 160. Error for the error of prediction, which is like, so minus the model, or it could be the other way around, doesn't really matter. So one, the model over predicted, the one model under predicted. Now we can do the error square, or the squared error, we call it. Why? Because the error can be in both positive and negative. So let's make sure that the sign doesn't play a role in determining the total error. And from here we do the mean squared error. So mean squared error. And now that we have squared it, we have to take the square off as well, right? So we do the root mean squared error, which is the root of this. So that's roughly how the model accuracy is calculated, and it's a very useful number, RMSE. So this tells me that this model's root mean squared error is 15, which means that on average the model would be making a plus minus 15 error in prediction. So we see that this model, the root mean squared error is quite high. It's 500 in a 5-fold cross validation. So this is the performance of the model here. Now, how do we know this is a good model or not? That's where we can try out different models. So instead of a, say, simple linear model, we can try out, say, a naive Bayes algorithm. if I start with a naive Bayes algorithm, there is an error because naive Bayes actually I made a mistake. Naive Bayes is more for classification, not predicting a numeric value. So let's actually look at another numeric value model. Yeah, we can look at k nearest neighbors. So k nearest neighbors, what it does is looks at nearest neighbors. Say it tries to figure out that whether the data it's trying to predict, it looks into the data set and looks at other data sets, like other data points where the prediction is made, and then picks a prediction from there. So it tries to find nearest neighbors and then makes a prediction based on nearest neighbors. So let's say how the nearest neighbors perform compared to, say, the linear regression. So when we compare this, so the RMSE for k nearest neighbor is actually much higher compared to linear regression, which means that linear regression does a better job than k nearest neighbors. In fact, this is where the model comparison matrix comes up, another very useful thing. So what it tells me is the probability that KNN does a better job than linear regression. And so the probability that MSE of KNN is statistically significantly higher than linear regression, and that probability is almost 99%. The other way of putting it is probability of linear regressions and RMSE is greater than KNN's MSE, is almost null, which means that they do a statistical test to confirm you that KNN has higher MSE 99.9% of the times compared to linear regression. We can actually make it RMSE, at which point KNN performs like as higher RMSE compared to linear regression almost all the time, which is a statistical proof that linear regression is better than KNN, at least for this data set. What about other data, like other models? How about, say, if I bring in trees, which is a recursive partitioning mechanism. I'll explain the trees a little bit later, but let's say I bring in a tree model and test it. Now what's happening? So tree still has a higher RMSE than linear regression, though the difference is not too much. So this number tells me that, first of all, again, KNN is having higher, more root mean squared error than tree almost 91.5% of the times. That means 8.5% of the times KNN does better than tree, but 91.5% of the times tree does better than KNN. But now if you're comparing tree with linear regression, something interesting happens. If you see that 98% of the times tree has an RMSE which is greater than linear regression, which means that tree gets underperformed by linear regression 98% of the times. Now, let's see what we get with other models. So another model is, instead of growing, okay, actually before we go to random forest, let's me show what tree looks like. So this is where we have a very handy tool called tree visualizer, tree viewer. So the way tree models are fit is something we call recursive partitioning. So let's actually zoom out the most actually, and let's reduce the width a lot as well here, and let's make it 2 levels. Start with, yeah, let's actually start with 2 levels. So what it does, the way trees work is, first of all, we start with the average spending of the whole data set, which is 1216 plus minus this, they are 1000. So the first thing that the tree does is, by the tree algorithm, it's figuring out that we can divide the total 1000 data we have into 2 groups. One group having high history, the other group having low or medium history. If you're high history, you automatically spend higher compared to low or medium history. Now, why history? Why not other variables? So here, what statistically they do, this algorithm works with, is something called information gain. So information gain means that it tries to see, it iteratively checks that what other variables impact amount spending. And it found out that history, if I divide by this grouping, that, you know, in one side we have high history, and in the other side we have low or medium history, then the information gain would be the highest. The differences of the separation of the spending would be the highest. So it starts with history. Now what happens with high history? Oops, it got expanded to all the levels. So let's make it easier for us. Let's click 3 levels. So if the customer is of high history, then they're checking salary. Let's increase the width a little bit and zoom a little bit as well for your readability. Here, better. So when the salary, if the person is of high history, then if the salary is more than 109,000 in a year, 35 instances are there who spend on average 3,192. If the salary is less than 109,000 a year, then the spending is this. Now, what about low and medium history? If the history is low, then the spending is this. If the history is medium, then the average spending is this. Now let's go to the next level. Now, in this case, so if it's high history and if the salary is greater than this number, we look at catalogs. If it's high history and the salary is less than this number, we also look at catalogs. Here, the third division among all of them are basically catalogs. The next level of division is after catalogs, some are looking at salaries, some are looking at catalogs. So we can divide the data set in this way, in a way that, only 1 or 2 instances remain in every leaf. So these are called leaves. So overall, this is a very good or a very useful method when we try to build models out of very complex relationships, because it does a step by step way of modeling. So it's very good at fitting complex lines. But tree method kind of fails when we try to fit models when the relationship is actually linear. At that point, linear regression does a better job than trees. Now, this is a tree, but then what is a forest? And my answer is very lame at this point. A forest is just a collection of trees. So what's a collection of trees? You can build a single tree out of the data set. Then what is a collection of trees? So here comes the idea that, instead of building a single model, why can't we build multiple models? Say we build multiple trees, each tree consisting of a subgroup or subset of the data set, smaller subset of the data set, and in various permutation combinations, you can use different smaller subsets of the data and then build a model or build a tree for each of them. And then using many of the trees, you build a forest and then use the forest to make a prediction. Now, the beauty of this is when you build a forest, some of the trees will be very accurate, some of them will be less accurate, and then the trees will be weighted based on their accuracies. It's part of something we call ensemble learning. And what ensemble learning is a new field where we talk about, why limit ourselves to one model only when we have computing power to build many models and then make predictions based on these models. And what if some of the models are good, some of the models are bad? The beauty of it is we are training our models based on existing data where my prediction variable, my y variable, is known to me. So I can test each of these models, and for each of these models, I can also test the error, the RMSE of each of these models. And then we can actually make our prediction based on weighting, based on the accuracy. Models that are more accurate will have more weightage. Models that are less accurate will have less weightage. And then they each will suggest a prediction. And then the weighted average prediction will be the prediction of all the models. That's what starts with random forest, which is a collection of many trees. Let's actually first check how many trees we want. Let's say I want to go a little wild. I want 100 trees. And now the forest of 100 trees is giving me RMSE, which is actually the lowest. So if I rank by RMSE, random forest does better than linear regression. In fact, if I compare random forest with KNN, then obviously random forest is the chance of random forest having more RMSE than KNN is 0. That means random forest will always outperform KNN. Random forest having a RMSE greater than 3 is 0.004, 0.4% of the times. So 4 out of 1,000 times, maybe 3 can beat a random forest, which is obvious because, random forest is the collection of all these trees. So definitely a random forest would be better than 3. Regression, so 2 out of 100 times, regression would do a better job than random forest. The rest of the time, 90 of the times, random forest would do a better job. That means that random forest is a better model at predicting in our case. Now, the fact that I talked about ensemble learning means that I'm going to show you that, say, for example, KNN is one algorithm through which we have, like, these models are using different philosophers of different algorithms. Linear regression does a different algorithm. Linear regression is fit based on OLS, ordinary least square, right? Reducing error among the predicted and the real values. KNN is based on neighbors. Tree is based on information gain. So what if we merge three algorithms together to a singular model which uses combinations of both linear regression, nearest neighbor algorithm, and the tree algorithm together? So this is another form of ensemble learning. We call them stacking. So in stacking, I can choose which models to stack, which models to combine. So I want to have a linear model as one of the learners. I want to have a nearest neighbor model as another learner. I want to have a random forest. You can ask me why we are not choosing a tree, because I mean, tree is already part of the set of random forest because it's using the tree algorithm either ways. Then we connect it to data. There is an error coming up. What is that error? Let's check. Data has no target variable. Oh, sorry. So I chose the direct data. So let's just remove this. Select columns. So now they have the target variable. It does slow down the process a little bit, yeah. And then we can evaluate how stacking does. Will take some time. So because it's merging all these models together. Now let's say how stacking did. Stacking did better than random forest, but here is the sad part of it. The RMSE of stacking and the RMSE of random forest are not very different. Stacking is just a little bit better than random forest. That's it. Nothing more. This tells me that maybe because stacking takes a lot of processing power, as you saw, it took more time. So in our data set, maybe random forest is the solution to make a prediction. Stacking could be done, but it does take a lot of processing power and gives me less improvements, both in terms of R square and RMSE. So, but again, remember that this might not be the case all the time. You have to be careful because this is one data set, which is where stacking doesn't give me much benefit compared to random forest. But you'll find many data sets where stacking might do a way better job than even random forests. Now, finally, I'll show one more one, which is basically the neural networks. So before we do neural networks, if you remember, I showed you how to pre-process the data because we need to do a lot of pre-processing before neural networks. So first of all, we do is pre-process the data. And we have already set up the pre-processing here. Let's not have the principal components, but the other ones. Because for neural networks, the input has to be a pre-processed data. We cannot just have any format because then there will be a lot of errors. And then we fit in a neural network. So we go to model, fit in a neural network. Here is a neural network being fit. So it's basically the pre-processed data as the data. That's good enough. And we can also decide 100 hidden layers. So that's a very deep neural network. And then we can test our neural network's performance. Unfortunately, I have a feeling you'll get a very erroneous prediction now. Yes, neural network has a much erroneous prediction. This is because at this point, we haven't properly cleaned our data for neural network. There's a lot of missing data there. And also because neural network cannot be used to compare, because what we are doing is, if you see, we are comparing neural network to regular normal data, but we're comparing processed data to regular normal data. So to compare apples to apples, we need to run these models in processed data and then see how neural network does compared to all other models. So that's the complexity with neural networks. Now that we know that random forest does a good job, let's put it separately here. And then we can also build predictions based on random forests. So we build predictions here. And what's going to happen is it's making the predictions based on random forests. Each of the amount spent. So this is the real amount spent, and this is the model-based amount spent for each of the data points. So we can build these predictions, and then we can export this data or save this data, and save it as predictions. So this is how we can choose to predict. Now, one interesting thing that Orange can do besides just fitting models is also explaining models, and I find that to be another very useful tool. Specifically, they have this widget called Explain. You can get this widget from widgets and then options and add-ons. Sorry. And from add-ons, permissions and so on, that's fine. If you go to add-ons, here you'll see Explain add-on, another very useful add-on here. Now, in here is a very useful function called Explain Feature Importance. So we can build this, bring this model here, and say based on, oh, and we need to connect the data as well. So what it does, because say in terms of linear regression or everything else, linear regression is explainable, but random forest, you can just use random forest to make a prediction, but how do you explain random forest? So this is how you explain a random forest. So what you do is you look at all the variables there is, and you see which of the ones have the highest impact on RMSE. So as you can see, salary has the highest impact on RMSE. Salary has the most increase in RMSE, followed by history, followed by catalogs, followed by location and children, which means that among the data I have, among the data we have, salary, history, catalogs, location, and children impact amount spending the most. And variables such as age, gender, married, or own home doesn't play much of a role in predicting amount spent. Another useful one is using the explain model widget. There it is. Now we first, so for the input of explain widget model, we need the model here, and we also need the data here. So it's building a model explanation. This does take some time, but it's again very useful. So if we converge here, so this gives me an idea that okay, how much of salary having input impact on model output. So the positive end of it and the high end of amount spent. So if salary is higher, it does impact on high amount spent, though the salary low has not that extreme impact. So it looks at symmetricality of how much, in which way my the spending amount is being impacted by each of the variables. For example, catalogs has a lot of positive impact, though it has some negative impact, whereas history low has a very high negative impact. History medium has some high negative impact, whereas history high has a very positive impact. It looks at how positive or negative impact each of the variables have. So that kind of summarizes what we can do in terms of machine learning in Orange as well. So I think today as well, I've seen flew through a lot of content and shared quite a lot of things we can do with Orange. I would want to pause it here, or actually end it here, because I'm afraid of giving you information overload. But I think this is, I would say, a very thorough and a good initial introduction to what Orange can do. And all of these, so I would highlight some limitations of Orange at this point. So Orange can be a little difficult to work with when there is a lot of data sets. So when the data sets size increases a little too much, then Orange can hang a lot. At which point, my suggestion is if you still want to use Orange, you can actually use a small sample of the data to work with Orange. That's one. The other thing is Orange can get make sure you have a good processing power before working with Orange, because it does take a lot of RAM. So for example, the reason I'm sharing a 1000 row data set here is because I know that if I share a 1 million row or a 10 billion row data set, 10 million row data set, it can work in normal spaces. But when I'm sharing my RAM power with Microsoft Teams, I know that it will get stuck. So it takes in a lot of data. So make sure you have enough RAM, RAM space open to work with Orange. But other than that, I consider this a very handy software to quickly do some analysis if you don't want to code. So with that, I'd like to end my sharing and open the floor for any questions, confusions, anything you have. So you can drop any questions or any feedbacks you have in the chat box as well. Or like last time, I think Ria got some WhatsApp messages as well with some questions. So if you can also send Neeti some questions if you have, and I'll be more than happy to answer. If there is none, I'd like to pass the floor to Neeti if you want to conclude the session.
Okay, sir. As there are no questions, I'll continue ahead. That was quite enthralling and inciting session right here. I would like to thank our speaker, Khan Muhammad Saqiful Alim sir, for taking out time from his busy schedule for us and conducting such an engrossing sessions. It was a pleasure having you. Thank you, sir. I would request the participants to fill up the feedback form to receive the certificate for completing this 2 days hands-on data exploration workshop. The link will be posted in the chat box. Now I would like to request Geeta ma'am to add few words. I would also request Neelam ma'am to add few words.
Thank you, Niti. Thank you so much, sir, for accepting our invitation and guiding our students about this software. I hope your health is fine now. Sir, you are on mute.
I say that it took a downturn last week, but thankfully I'm quite recovered now. So thank you so much.
It was a nice session, sir. Actually, I missed a bit of it. My phone got off, actually.
You're most
It was
welcome.
a
And I
nice
think there's
session.
there's a
Yesterday
recording.
also
So
I listened to many things. And it is a new area. Thank you, sir.
you're most welcome.
Niti, we will have a group photo.
Ma'am, there is one question in the WhatsApp group. Sir, there's one question. What type of
Sure.
businesses actually use Orange?
Actually, Orange is being used by quite a lot of businesses across few industries, I would say. So I know of H&M. So some of the offices of H&M uses Orange for its managers. Then I know of few banks in Singapore, and I know that the Bioinformatics lab in Duke University, as well as the Duke NUS lab, they use Orange to do quite a lot of their healthcare research. So, I mean, it is a tool that has been used quite extensive. Like, I won't say quite extensively because it's still, I mean, not a lot of people know about it, but those who know quite use it a lot in across many different industries. Very recently, I heard of like Singapore Airlines using Orange as analyzing some of its small like data and data processing stuff.
One more question, sir. Can we do deep learning with Orange?
Yes, we can do deep learning in Orange, but so there are image analytics tools there as well. So for neural networks, there is a different add-on for Orange as well. So some of the basic deep learning can be done on Orange, but I think when you're going for like, transformers, or when you're going for like LSTM, then I think Orange would take a lot more time, in which case you can also shift to Python or coding. That's like more advised.
One more question, sir. If we want to do projects with Orange, from where can we download sample data?
So I think there are a few places you can actually get data from. So what I'm going to do for your help, I think I'm going to share the I will share a list of places where you can get a lot of good data from to Ria's WhatsApp, so that she can share with the group. But to mention here, I think one source of good data is Kaggle. So I'm going to write it here as well for your benefit. So it's Kaggle. So you can go to Kaggle and find quite a lot of data there. And then there is University of UCI Machine Learning Repository. That's another good source of data. Then another very good source of data is Google datasets. They have some free datasets there. Not that Google datasets such. They do have the Google free database actually. So sorry. And two other interesting sources of data are Makeover Mondays, and the other one is Something Tuesdays. I'll share the link. I'll share the link with Ria so that you can take that out. I think Niranjan is also asking a question. Is Orange available in API form which I can add to my application? I don't think so. They haven't yet opened up for production. So you would need APIs for deploying machine learning models, which I think Orange still is not equipped with. You can do basic analysis and model fitting with Orange, but in terms of building deployable models or using APIs, I still don't think Orange can help you with that.
So one more question. How can we convert data in sound form to Excel or table form?
That you would need help of voice analytics tools or voice analytics libraries, which also come from Python's libraries such as Keras, or even PyTorch. So you would need Python for converting that. Oh, TensorFlow, another library that you can use.
Well, that was an engrossing exchange of questions, and I'm sure our audience present here is content with the answers. I would like to request everyone to switch on the camera for a quick photograph. Is the screenshot taken, Ria?
Niti, it's
Yes.
done.
Okay, thank you. As we come to the end of today's session, I would like to thank all the faculty members, Biomedical Department of VIT, conveners, and you participants for making this workshop a successful one. Also, Biomedical Department of VIT and Team Impulse have conducted fun events. Kindly register and participate to relish these events and embark your 2022 noteworthy. Thank you so much, everyone. Hoping to see you soon. Take care, stay safe.
There is an event on surgical robots on 26th. We will send you the brochure.
Yes, ma'am. We will float it on the group and all the participants also.
Yes.